Now let us see what is Diels-Alder reaction. Very interesting reaction because you are making new carbon-carbon bond, okay, and it is having lots of synthetic application in, in organic synthesis, okay, and lots of pharmaceutical products and agrochemicals and lot more. Now let us see what is Diels-Alder reaction. Okay, now in Diels-Alder reaction, now we'll see first what is Diels-Alder reaction. In Diels-Alder reaction, you have a diene, okay, and dienophile. Now diene, okay, in very simple manner, you can take 1, 3 butadiene. Very simple diene I'm taking, okay, and that too should be cis. Then you have dienophile. Okay, so this is your diene, and dienophile is having two bond. Okay, so double bond compound. This is, let's say very simple, ethene. This is your dienophile. Okay, now consider a diene like this. Okay, and if you take a dienophile, very well known reaction, so the product you will get here is this is your Diels-Alder adduct. Okay, this is your final product. Okay, this is your diene, and this is your dienophile. This reaction is generally favorable under thermally. There are many reactions which takes place at room temperature. Also, some reactions take place with the help of catalyst, which is generally Lewis acid. So this is the Diels-Alder reaction. In Diels-Alder reaction, you have various types of Diels-Alder reaction. One is normal electron demand. Okay, second you can say inverse electron demand, and in third case it is neutral. That is the diene or dienophile, neutral electron demand, and it is neither normal neither inverse. Okay, it's a normal demand Diels-Alder reaction in which highest occupied molecular orbital of diene and lowest unoccupied molecular orbital of dienophile interact. This will get a kind of normal electron Diels-Alder reaction. For example, uh, uh, now here generally in this case dienophile have electron withdrawing group in it. This I will show you now. Okay, now first is normal electron Diels-Alder reaction. Second is inverse electron demand Diels-Alder reaction. In this case, you have, now here it is reversed. LUMO of diene and HOMO of dienophile. So this is your inverse electron demand. Inverse means here dienophile will have electron donating group on it, like oxygen, nitrogen, sulfur, and so on. In that case, it is neutral one, neutral electron demand, Diels-Alder reaction. these reactions are neutral electron demand Diels-Alder reaction because either LUMO or HOMO or LUMO of dyne and dienophile will interact. So there will be not much or not energy much difference between HOMO of uh, dyne and LUMO of dienophile or vice versa. So the energy gap is there is no difference. Either it can react with LUMO of um, dyne and HOMO of dienophile or HOMO of dyne and LUMO of dienophile. So there is not much difference in this. Either of these can interact with any of this. If you are taking LUMO of dyne, so it will interact with HOMO of dienophile. If you take HOMO of dyne, it will interact with LUMO of dyne. So there will be no difference between either of these interactions. This is almost having same energy level, so there will be no difference, and that is why it is called as neutral electron demand. Okay, now we'll see what is this is we'll see by using frontier molecular orbitals. This we'll see by using frontier molecular orbitals of dyne and dienophile. Okay, so interaction will take place in this manner. Okay, now let us discuss Diels-Alder reaction. Diels-Alder reaction and the rates of Diels-Alder reaction. How to determine the rates of Diels-Alder reaction and how to determine what kind of reaction it is. Now, in general case, dynes are generally electron rich and dienophiles are electron poor. So this kind of reactions are called as normal electron demand Diels-Alder reaction. Normal electron demand Diels-Alder reaction. And when dienophile is rich in electron and dyne is electron poor, then that is called as inverse electron demand Diels-Alder reaction. The inverse electron demand Diels-Alder reaction. How it works? Now let us see. Now suppose this is a dyne and dienophile, and dienophile is having an electron withdrawing group. Dienophile is having an electron withdrawing group. Now this leads to decrease in the HOMO-LUMO energy of dienophile. Now here if you see the highest occupied molecular orbital of dyne and lowest unoccupied molecular orbital of dienophile, the energy difference is less. Now I'm giving it name as P1. P1 is less is as compared to highest occupied molecular orbital and lowest unoccupied molecular orbital of dyne. This is the energy gap in this is more, but if you see HOMO of dyne and LUMO of dienophile, the energy difference is less. So this reaction is you can consider as normal electron demand. Normal electron demand. Okay. Now I'm taking directly third case. Here the electron donating group on the dienophile and if you see the HOMO-LUMO energy of dienophile, it is bit higher than or you can say much higher than the case number 1, that is this one. It is higher. So if you see the highest occupied molecular orbital of dyne and lowest unoccupied molecular orbital of dienophile, the energy difference is very large. This is very large as compared to the previous case, that is the case number 1. The energy difference is very large. So here another possibility is that you can have the HOMO-LUMO interaction of dienophile and dyne respectively, that is HOMO of dienophile and LUMO of dyne. So this interaction is having much less energy than the HOMO of dyne and LUMO of dienophile. So here this case it is inverse electron demand Diels-Alder reaction. This is your normal electron demand and this is inverse electron demand. Now come to the case number 2. Here you have hydrogen. Hydrogen is not electron donating, not electron poor. Now if you see the energy difference between HOMO of dyne and LUMO of dienophile, okay, this is the energy gap, and even if you see the energy gap between HOMO of dinophile and LUMO of dime, again it is having this much energy. So there is not much difference in the energy in the case number 2. So this is you can consider as neutral. Okay, the rate of reaction also depends on this. Okay, but there are other factors also on which the rate of reaction in Diels-Alder reaction depends. Okay, so some reactions are normal electron demand, as the case number 1. This is your normal electron demand. Case number 3 is your inverse electron demand Diels-Alder reaction, and the second one is neutral one. Okay, so this is the Diels-Alder reaction, or brief discussion about Diels-Alder reaction using frontier molecular orbitals. Is that clear?